talking about. And inference is when you don't know something, but you take some evidence and you make a calculation or an estimation. And this is an inference. Today we'll be talking about population proportions. I didn't leave myself much room at the top of that curve. So up here, this guy is going to be p hat. If we're talking about proportions, it's not x bar, it's going to be p hat. And out here, we have our critical values. Critical values. So there's a plus and a minus of the critical values. And I know this is kind of small, I apologize. This is going to be, this is p hat plus our margin of error, ME. And this is going to be our p hat minus our margin of error. So p hat's the middle, margin of error is plus or minus some amount to get to our critical values. M or ME. It's hard for me to draw an M now without making it look like mu, but margin of error. So common critical values. These are our critical values. We use Z star, which is absolutely no different than Z except that it's a plus and a minus. Z star is your plus or minus Z score. Okay. So for a 90% confidence interval, this gives us plus or minus Z star, which is 1.645. So that's a little more accurate than what you could pull off the table at. You'd either say it's 1.64 or 1.65, but it's actually halfway between those. For 95%, a little more accurate than 2 and negative 2 is going to be plus or minus 1.96. We've seen that one a few times already in our notes. And for our 99% confidence interval, this is plus or minus 2.576. So you'll see Z star is a new symbol, M or ME is a new symbol. But the star, don't let that freak you out, it's just plus or minus. So if we don't know any parameters, we can't really do the standard deviation the way we have in the past. So now we have something called standard error. And we'll go of a sample proportion. We say SE of p hat. So instead of sigma p hat, it's standard error of p hat. And it's going to look pretty similar. It's p hat times 1 minus p hat all over n. So why would we use P and we are using P hat. Any thoughts on that? Here's why. Because we're going to be making an inference about what P is. P is a population proportion that is unknown and probably unknowable. So how can we do a calculation with a value that we will never really know and haven't been given? We can't. So we have to substitute P hat where P used to be. So here's my general rule for this. When P is unknown, and I'm going to say that's almost always, we use P hat in our calculations. Or how about we substitute? So far so good? So now we've eliminated one thing. We don't have to identify P anymore. You don't have it. You get to figure it out. So if I draw this out again, I got P hat here. That's some proportion that we know because it came from a sample. And we're going to be plus Z star times the standard error of P hat, and minus Z star times the standard error of P hat. So we're just saying P hat plus how many standard deviations away and that value of the standard deviation itself. How much is one standard deviation? And minus the z-score, how many standard deviations, and the value of one standard deviation. So the formula for an interval is P hat plus or minus Z star. Now the book will say standard error of P hat like I've put in there, but let's just put this in and go P hat times 1 minus P hat all over n. That's the moneymaker for today, guys. Before we step away from that, I want you to understand that this is the center. This refers to how wide is our interval, 80, 90, 95, 99, whatever. And this is your standard deviation. So what this whole thing is here, that's your margin of error. Right here, this is your margin of error. P hat plus this, and P hat minus this. It's the margin of error. If you see it that way, I think things become a little more, at least to me, it became clearer. Margin of error. P hat plus and minus the margin of error. Now we calculate margin of error differently depending on what we're given, but this is for proportions. Everybody good? All right, conditions of inference for proportion. It has to come from a random sample. The data has to come from some random sampling. Usually that's given, but if it's given, you can't just assume that the reader understands you know that. You'd have to say SRS is given, or sometimes we assume it. The 10% rule has to be in place. And the third one, is it normal? If it's a proportion, the central limit theorem does not apply. You have to check, does n times, wait a minute, I don't have p anymore. What do I use? P hat, good. Is n times p hat greater than or equal to 10? And n times 1 minus p hat, is that also greater than or equal to 10? So the only change there is we don't have p, so we just substitute p hat and call it good. Conditions. These have to be met before you can do any kind of inference. So let's look at a couple problems. Actually, I have a few problems that I want to go through today because it's a fairly long set of problems, but I also want you to see some good examples. So on page 522, if you want to go there, number 35, and talk about selling online. So this problem says that according to a recent Pew Research Center, which, by the way, Pew Research, those guys usually do a pretty good job of statistics, many American adults have made money by selling something online. In a random sample of 4,579 American adults, 914 said they earned money selling online. And by the way, SRS was given. Assume conditions for inference are met. Determine the critical value z-score for a 98% confidence interval. We don't know the z-star value for 98%. By the way, I have a cheat sheet for you. I don't know if you noticed or not, but I added it to the board. All right, these are our three most commons, but we need to be able to calculate if we're asked something else. So we're looking for a 98% confidence interval. And we want our z-star values, but before we do that, what's p hat? This is all the data I'm given. No? That's correct. The 914 that sell online compared to the total. And I don't know what that works out to. I'll worry about that later. So where am I at here? Right, determine the critical values for a 98% confidence interval. So what you need to do for a 98% confidence interval, I think it makes sense to kind of just do a quick drawing. If I've got 98% in the middle, how much are in each tail? 1%, good. So to get the z-star value, I can do one of two things. I can either look on the negative side and find 1%, or I can look on the positive side and find 99%, right? Because I've got the 98 plus the 1 left of that. I think it's easiest to go onto the negative side and look for the 1%, as close as I can get it. Let's see, it's between these two guys here. So negative 2.32 or negative 2.33. This is closer. I'm going to go with negative 2.33. And what can you tell me about this one? Can you tell me what this one is without looking it up? 2.33, yeah. So you really only have to look up 1. So our z-star for this is plus or minus 2.33. By the way, this appears to be 0.1996, which I will call about 20%. Let's go with 20% for the p-hat. Bless you. So B asks us to construct a 98% confidence interval for the proportion of all American adults who would report having earned money by selling something online in the previous year. Okay, well, that's going to be our p-hat value plus or minus z-star times the standard deviation of the sample proportion. So that's going to be my p-hat times 1 minus p-hat all over n. So I'm using that formula that I had on the other page. P-hat, z-star, standard error of, oops, I forgot. I know n. Why am I putting an n there? Getting behind myself. This should be 4579. So these are fairly easy to calculate on the calculator. If we here's what I do. I always do the minus first, because when you're answering a question, you usually give the smaller value first and then the larger value. So I'm going to go 0.2 minus 2.33, and then square root of 0.2. 1 minus 0.2, that's going to be 0.8. Let's see, times 0.8. Divided by 4579. I don't really need any parentheses in there. Order of operations works out just fine the way it is. And so that gives me an interval, my lower interval, of about 0.186. And then to do the plus, I just come up here and copy that and just change the minus to a plus. You don't have to delete it, you just type over it. And so that's 0.214. Are you able to make that work? And these values look like they make sense. I mean, 0.2 is between those two. That's what we're expecting. So C asks us to interpret the interval. So we are what percent confident? 98 in this case, right? 98% confident. The true, what's the parameter we're looking for? We doing counts or proportions here? Proportions. The true proportion hang on, let's get some context in there. Of Americans who sell online is between 0.186 and 0.214. So between about 18.6 and 21.4%. So what's the probability that it falls between these two? Nope. Ben, did I hear? Did I hear an answer? No? No? What's the probability the true proportion falls between these two? And maybe 0 or 1. Right. It either does or it doesn't. We don't know which. Right? So we're making an inference. This is our best guess as to where the true proportion lies of all American citizens. But it could be less, it could be more, or it could be in between. We don't know. So the probability, remember, probability doesn't work for inference. The probability is maybe. It's either 0 or 1. Okay, let's look at number 45. '45 is on the next page, 523. It says food fight. It's talking about organic produce. It says in a 2016 survey, 1,480 randomly selected U.S. adults found 55% of respondents agreed with the following statement. Organic produce is better for health than conventionally grown produce. Okay, so here's what I've got. SRS. I've got N equals 1480. And P hat is 55%, 0.55. That's what I gathered out of that. Construct and interpret a 99% confidence interval for the proportion of all adults who think the organic produce is better for health. So we're looking for P. So we need our conditions. SRS, that's given, or just a random sample given. 10% rule. Is it reasonable that 10% of all Americans, I think that's who was in the survey, all U.S. adults is greater than 1480? That's a way of kind of putting the context into it without getting too crazy. Does that seem reasonable? Yes. Yeah, that's a fair one to assume. And N times P, or sorry, N times P hat, 1480 times 0.55. Is that going to be greater than or equal to 10, you think? Yeah. You don't need to do the math for me there. But I do think you need to put the numbers in there. Oops, 1480. If the math is close, though, do the math. So it's normal. Alright, so we've met our conditions. These are the three we need to meet. SRS, just general rule. This allows us to standardize, and this allows us, this allows us to take the standard deviation, and this allows us to standardize. Alright, so we're talking a 99% confidence interval, was that right? Yeah, 99%. So this is going to be 0.55 plus or minus 2.576. That's the value on the board for 99%, times the standard deviation, 0.55, times 1 minus 0.55, or you can just put 4 or 5 there if you want, divided by 1480. This is the middle, plus and minus the margin of error. So 0.55 minus 2.576. I get 0.517. I'll copy that and change the minus to plus. Alright, so far so good. So we have to now answer in context. We, I don't know why it's always we, everybody gets included. We are 99% confident the true what? Proportion, good, of U.S. adults who prefer or who believe organic is better for you is between 517, 0.583. So does this give convincing evidence that a majority of U.S. adults think that organic is better for you? No? Why not, Sydney? Point 513, no, 517. I'm going to disagree with Sydney on this one. I think this does give us convincing evidence. Because where would 50% fall? Or 50 plus 1. 50% plus 1. Where that be way out over here somewhere? So our 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 majority is just one more than 50%. That puts it in the tail. I agree that that generally is convincing evidence, but we're kind of looking at it from another point of view. I'm saying that it's convincing evidence because it's in the tail and it's really low, and the majority of people, majority of our samples should fall well above the 50% plus 1 range. Does that make sense? Well, you got to get the majority, right? If there's 1 million people, a majority would be 500,001, right? 50% plus 1 more would be a majority. So I'm saying the 50% plus 1 more person is going to fall way over here. Yeah, it's going to be way out over here somewhere. So I think it is convincing. I would say that it is convincing because it's in the tail, right? It's in the tail. It's convincing. Okay. All right. There was one more I think I wanted to go through. 49 is school vouchers. Was a little left incomplete, but that's okay. Let's go 49 here. So in this problem, they say that the small pilot study estimated that 44% of all American adults agreed that parents should be given vouchers that are good for education at any time, at any public or private education or school of their choice. So 44% is our p hat who think that vouchers should be given. How large a random sample is required to obtain a margin of error of at most 0.03 with a 99% confidence interval? I didn't give this to you in your notes because I wanted to do this one as a problem. But the question is, the margin of error has to be less than or equal to 0.03. That's what they want us to do, with a 99% confidence interval. All right, so we're really just looking at the margin of error. So 0.03, this is A, by the way, 0.03 has to be greater than or equal to. The 99% confidence interval is going to have a z-star of 2.576. This is z-star. But I'm not using the plus or minus this time, just the z itself. Times 0.44, square root of 0.44 times 1 minus 0.44, all over n. So the question is, how big does n have to be for this to be true? So we have a fairly simple algebraic problem here to solve. What should I do first? Hey guys, up here is some stuff that you might get a question on. I want you to be able to solve it. How should I start solving this equation for n? I wouldn't do that yet because we have this thing sitting outside of the root. Can we get rid of this first? Let's divide by 2.576. So when I divide this, I get about 0.012. But I'm going to leave that value in the calculator. So I'm going to go .03 divided by 2.576. And I've rounded for my work purposes, but I'm going to leave that value in the calculator. And so then I've got square root of 0.44, 1 minus 0.44 over n. Now I think we should square. So I'm going to square both sides. So I'm going to take this value and I'm going to square it. I'm not going to round it out. So I'm just going to go x squared. And again, I'm going to leave that value. It's about 0.0000136. It's greater than or equal to 0.44 times 1 minus 0.44. Or you can put 56 in there at this point. Sure. All right. Now what? Multiply by n. Good. Yeah. Let's multiply by n. Get that out of the denominator. So this is going to be n times point this thing. And then the last step is going to be to divide, right? Divide both sides by that mess. So here's what I'm going to do in the calculator. I'm going to take this value and I'm going to first start by calculating this. Oops. 44 times 0.56, and then I'm going to divide that by this thing that I have in the calculator, but I'm not going to retype it. I'm going to copy it and bring it down. So I get that this is n is greater than or equal to 1816.7273. But that's a problem, because we're talking about people. And although it's possible, it's really not socially acceptable to have 0.73 of a person, right? How do you get there? The only way I can think of is, they're all messy, but I'm thinking like chainsaw, all right? Okay? It just isn't really socially acceptable to go cutting out 0.73 of a person to make our stats work out right. So we either have to round up or we have to round down. Which one do we do?
Round up.
Round up? Is it still going to make our inequality true? I don't know. Let's see. So we're going to say that n has to be greater than or equal to 1817. Let's check it. If I put in 1817 here, do I get a value that's less than 0.03? So I'm going to go 2.576 times the square root of 0.44 times 0.56 divided by, what did I say, 1817? If my answer is less than 0.03, we're golden. If it's not, I need to round down. Okay? All right. Good call. Round up.
I just thought of it as like, when you have 0.73 of a person, right? Are you going to count the non-person?
That's true, but what if that came out to be 0.01 of a person? What if this wasn't 1816.73, but 1816.01? Well, then you're taking maybe a finger off, right? You're saying that's not so bad? It's socially acceptable for the stats to take a finger off, but not like a 0.73 of a person. So here's the point that I'm trying to make. if I put in 16, if we rounded down, because I agree, there would be times where rounding down mathematically would make sense, but does it work in the problem? And the answer would be no, it doesn't. You have to round up when we're talking about people. Always.
Always, right?
Always round up when we're talking about people. Yep, because otherwise, now my inequality is not true because that's not less than the value that we're trying to find. Does that make sense? Round up when we're talking about people, okay? All right, so there we go. People, round up. Okay, that's enough of me talking.